Hi, I'm Eagle. I'm a data science living in London, and in this video I'm going to explain to you what the gamma distribution is. This distribution is used a lot, particularly when modelling claim severity in insurance, so it's definitely a concept well worth knowing if you're a data scientist. The things we'll cover in this video are what is a gamma distribution, deriving from first principles, and a basic example in Python. So let's get into it. So let's start with quickly recapping over where the gamma distribution really comes from. So it comes from something called the exponential distribution, which is something I did my previous video on, so feel free to check that out if you want more information. But the exponential distribution infers the probability of the waiting time between events in a Poisson process. The Poisson process is something where we expect a number of rates to happen in a certain time period. Again, I did a video on the Poisson distributions, so I won't spend too much time over in this video. So if you want to learn more about that, make sure to check it out. I've linked them on the screen here so you can visit them both. Now, the gamma distribution is basically an extension of the exponential distribution, and what it's saying is that, the exponential distribution only infers the probability of until the first event happens, but a gamma distribution infers the probability until the nth event happens. So you can see it's kind of like a generalization and extending what we're trying to calculate here into n times instead of just one time. So we can derive the gamma distribution by saying we want to wait a certain time t, big T, for the nth event to happen. For the gamma distribution, in this case, t is a random variable that we want to calculate. This means we need n-1 events to happen in some sort of other time t. So mathematically, what we have is this. What we're saying is we want the probability of, essentially of t being greater than t. So we're saying, again, it's hard to differentiate between big and small t in this case. But what we're saying is that we want to look at the probability of 0 events, or 1 event, or 2 events, or 3 events happening in time n-1 events in time t. And we can take that away because then we know whatever's left over must be the probability of waiting t events for the last one to happen. Again, this is quite, if you read through this, you kind of make sense in your head. It's not too complicated, but all we're saying is we want to work out the probability of n-1 events happening in a certain time interval, and then we can simply do 1 minus that to work out how long we have to wait, or the probability of waiting until the nth event. Now, all we need to do, like I said, sum up these probabilities here, and the way we sum up these probabilities is using the Poisson distribution. So the Poisson distribution looks like this, where lambda is the rate parameter, n is the number of events, and t is the time period we're waiting. So all we're saying is, what is the probability of getting 0 events in that time interval, 1 event in that time interval, 2 events in that time interval, all the way to n-1 events. And that is the goal of the summation. And we simply take the 1 minus it, so we get to our value of waiting big T until nth event. Again, I hope this makes sense. If you just ponder over this for a while, you probably understand it. It's not too complicated. It's just a lot of rewriting and kind of manipulating the equations to get into a format that allows us to calculate the PDF of the gamma distribution. So the above formula here is something called a cumulative distribution function, or the CDF. And to extract the probability density function is a known result in statistics that all we have to do is differentiate the CDF with respect to the random variable. In this case, t is our random variable. And this is how we do it. So the PDF, which is equal to the derivative with respect to t of this formula above here. Now, this derivative, to be honest, is quite exhaustive, and to save us making this video seem more like a maths lecture, I've kind of omitted it. However, I've linked this whole presentation in the description below, and in here I have linked also the full kind of derivation behind this derivative here, so you can check it out if you're interested. Like I said, I don't want this to be a maths lecture, and to be honest, we all know how to do differentiation. It's just a bit tedious to write it out in a slideshow for no reason. But again, you can check it out here if you're interested in looking at a full one, or even better, try it yourself. Try and derive this formula yourself. Be quite interesting. Anyway, so by doing that derivative, we find the final version of PDF as this, and this is basically a gamma PDF. This is what a gamma distribution looks like. So lambda is expected rate of events. Again, this comes from Poisson distribution that you can check out in my previous video. And n is the number of events waiting for. And that's all there is to it. This is the gamma distribution, or the gamma PDF function. And that's kind of like, this kind of characterizes the gamma distribution. Now you may be wondering, why is it called the gamma distribution? Well, there's a good reason for it. It is this formula here, n minus 1 lambda factorial is called the gamma function. And this is basically the denominator of the gamma PDF we showed in a previous slide. And so here, gamma is a Greek letter, and so we can rewrite PDF using it like this. So we replace the denominator with the gamma function. And that's the reason it's called the gamma distribution. Nothing really too fancy, more just it has that gamma Greek letter attached to it, which makes it called the gamma distribution. So let's go quickly over an example plot. So this plot shows us what is a waiting time until the third event, given various values of lambda. So the expected waiting time is 1 over lambda. And so you can see as lambda increases, our waiting time will decrease, which makes sense, right? If we expect an event to happen more frequently, then therefore the waiting time until the event happens will be less. And so, as we can see here, as lambda gets smaller, the expected time between events increases. So as lambda, lambda 2 is the blue line, orange is lambda 1, and green is lambda 0.5. As we decrease the rate of events happening, our waiting time probability increases. So you see the mean here, or the peak is around 5, here is about 2.5, and here is about, whatever that is, 0.5. And so all we're saying is the waiting time until the waiting time for events will increase as the rate will decrease, which is quite an intuitive result, right? Nothing too complicated there, but that's the main gist behind the gamma distribution. Another useful thing about a gamma distribution is that it's bounded at 0, which is really, really important, particularly for certain regression tasks you may find in machine learning, where your output, your target variable, can only take on positive values or positive continuous values. In this case, a gamma distribution is really useful for that because it is bounded at 0, so you will never get any negative outcomes. So I hope you enjoyed this video. Again, it was fairly short, more all about the intuition behind the gamma distribution and where it comes from. It kind of, adds on to the Poisson and then to the exponential distribution. So I really highly recommend you check out those videos to get a full intuition about what we did here. I've also got this whole presentation in blog format in my Medium page, so I'll link that in the description below, but make sure to check that out. That'll give you some more information and another way of digesting the material that will help in your learning. Also, I've got my socials here, so if you're interested in learning more about data science, subscribe to this YouTube channel. My GitHub's got lots of resources as well, and I also have a Twitter account which I tweet some data science things here and there. I also have a newsletter which I write every Monday. That's all about data science tips and tricks about my personal experiences within the field. So like I said, if you enjoyed this video and want to learn more about data science and statistics, then make sure to check out other videos on this channel. Also to like, comment and subscribe, and I'll see you in the next one.